One of the situations that we haven't talked about is what's called forced resonance. So resonance is where you have a system, and again, we're going to be studying systems mx double prime plus cx prime plus kx equals whatever your external forces are going to be, f of t. And forced resonance is where the external force is periodic. It's going to be a sine or cosine curve. So it's going to be something like some initial value f naught times cosine of, typically we use gamma t. So cosine of gamma t. And here the idea is we're going to try and solve this. This turns out to be exactly the case of being a second order linear constant coefficients, but non-homogeneous equation. So this is right up our alley here and something that we can solve with no problem really. So what I want to do is I want to concentrate on simple harmonic motion with forced resonance added to it. And then we'll describe physical systems that arise. So I'll give you kind of an idea of what that might look like. And then, yeah, then we'll go from there. So this again is called resonance, or sometimes forced resonance. And so what we're going to do is we're going to assume that we just have simple harmonic motion. So that means no dampener. And we're going to let, as usual, omega squared be k over m. So this is going to become, this is the same as x double prime plus omega squared x equals f naught times cosine of gamma t. I'm still going to use, this term I haven't told you what it is, so let's just absorb the m into it. It's not really going to matter, it's just some constant. But this is simple harmonic motion with forced resonance. And it turns out that solving this is going to break into two cases. So the first case is that if omega is not equal to gamma, so here omega is going to be some value, you're going to get a solution. So here your complementary solution is going to be something like C1 cosine of omega t plus C2 sine of omega t. And if the input here, if this gamma is going to be different than omega, then you're not going to have any repeated solutions. You don't have to do anything fancy. Your particular solution is just going to be something like a times cosine of gamma t. And then your general solution is going to be the complementary plus a particular solution. So C1 cosine of omega t plus C2 sine of omega t plus a times cosine of gamma t. Okay, and so here forced resonance is basically you're going to have that simple harmonic motion like you had before. So you imagine you're like, maybe you have the spring situation where you have a spring dangling and you're going to pull it down and then it'll move back and forth at a regular rate. Here, if we have a forced resonance, what that means is that there's going to be an extra force that's going to be applied, that it'll be periodic. And so what that generally looks like is without, so with no resonance, this is going to look something like, something like that, where it's going to have kind of a regular sum of cosine and sine terms. It probably won't be that boring, actually. If you're adding a cosine and a sine term together, it'll probably look something more closely like this, where it'll have possibly two crests, so something like that. And then if you're going to add in an external force, that can just make it go even worse. So this will just make it just a little bit more chaotic. So it'll be something like that, and then it'll be periodic. Okay, so that's the idea. So that's forced resonance, and again, you're just adding kind of a forced periodic external force to that mass system. Okay, so that's the first case. The last thing to talk about is what's going to be called forced oscillations in resonance. And this is the scenario where your external force is going to be the same as one of the functions that appeared in the complementary solution. So the complementary solution will be the same as before, C1 cosine of omega t plus C2 sine of omega t. So this tells you how this is going to act. So it's going to act as some sort of sum of cosine and sine waves. So it'll be periodic, with a certain period, with period t, where t is 2 pi over, so all the stuff that we talked about before, t is 2 pi over omega. And it's going to be periodic with period t, and it's going to be the sum of these sine and cosine curves. So you can, pop these into a graphing calculator and get much nicer pictures, but it'll be periodic with period. I'm just making stuff up here. But it'll look something like, maybe something like this. Okay, just as an example here. So again, and then this will repeat. It'll look something like that. Okay, so it'll be periodic with period t. So that's what happens when there's no external force. But if there is an external force and the force is some sort of cosine term, where this omega naught here is the same as this omega here, then you're going to get what's called a positive feedback loop. And so what's going to happen here is that you're going to have the same complementary solution, but now you're going to have a particular solution that's going to look very similar, or at least it would if we didn't add another term in front. So you're going to have a particular solution that's going to be something like a constant times t cosine of omega t plus, so I need to write this a little better. So you could have a times t cosine of omega t plus b t sine of omega t. Okay, and here what's going to happen is that the dominant term is going to be the particular solution, because as t goes to infinity, this is going to behave somewhere like somewhere between t and minus t, because cosine and sine go between 1 and minus 1. So this is really going to go between something like a plus b times t and a plus b times minus t. So anyway, so you're going to have some sort of lines that this is going to live between, and then the function is going to kind of bounce back and forth between these with positive feedback. So again, the idea is that the way that the motion of this mass is moving, if the force that's being input on the system is going to have that same value, then what's going to happen is the sine and the cosine waves are going to add together, and the amplitude of the waves is going to increase. And so you get this behavior. So this is kind of that positive feedback loop, which is why that sound gets louder and louder. Like if you ever have a microphone and the input and the output are similar sounds, or if you have a microphone and you get it too close to the speaker is picking up the sounds that it's spitting out of the microphone. So it's kind of this positive feedback loop. And that's basically what's happening when your external force is this cosine of omega t, where this is the same omega as here, right? You get that positive feedback loop, and the amplitude gets louder and louder and louder. The sine waves and cosine waves get added together. And so the amplitude increases. So that's basically what's happening here. So I think this is everything I wanted to say about positive feedback. And I think this is actually everything I wanted to say about chapter 5. Okay, so this is positive feedback loops. So we talked about movement of a mass on a spring, including when we had a dash pot. We talked about what it means to have an external force. We talked about how to solve all of these when there's no external force. And finally, we've talked about just in the previous video, forced oscillations and forced resonance. Okay, so I think that's everything I wanted to say about anything from chapter 5. With one caveat, we've been talking about movement of a mass along a spring, but it's striking that actually some of the electric engineering equations, like Kirchhoff's laws, basically have the same format as these laws of motion. And so you get these kind of second order systems, right? You get a y double prime plus by prime plus cy equals, again, maybe you have some sort of external force again, but it's really striking that there's a big similarity between movement of mass on a spring and electricity, which on its face seem like completely different phenomenon, and yet they behave similarly according to differential equations, right? So there's a lot that we could also say about electrical engineering and some applications of Kirchhoff's laws and inductance and resistance and all that, but they're basically the same equations that we had as before. It's just, I think, very interesting that this completely different scenario basically satisfies the same differential equations, okay, as this physical mass spring system. Okay, so anyways, for what it's worth. So if you're interested in reading any more about this, there's lots more in the book in chapter 5. Okay, so I'll leave that to you to look up. For now, what we're going to do is we're going to turn to power series. Okay, so we'll start chapter 6.